All right. So, short video. I promise, I think I promise, or I promise that I think, I don't know, that it'll be a short video. Because, the other videos I've made in this series, I guess, this playlist, whatever you want to call it, those go over kind of like the big picture stuff. This is just a, like, sample problem, right? And I'll explain, of course, what I'm doing. But it's more about, like, okay, so you want to know how to do these problems, right? It's one thing to have an idea of the theory, but you want the practical, can I find the answer, right? Pretty helpful, I would say. So if we look at this, let me see, I'm trying to move the mouse. There we go. Okay, there we go. Aha. I have a problem here that says, okay, decomposition of calcium carbonate, right? So it gives you the reaction there, tells you the phases, right? We obviously want to make sure it's balanced. Hopefully you're looking at this and saying, that appears to be balanced, right? But always make sure. And in this case, you're given delta H and you're given delta S for the reaction. In the past, right, or rather even now, you could, of course, get these numbers instead of being given them, right? You could look up what's the heat of formation of calcium carbonate, what's the heat of formation of calcium oxide, right? You're going to get a number that's probably either exactly that or very close, right? There can be some discrepancy with numbers, but it should be pretty darn close to that, okay? And the same thing for delta S, the change in entropy. But anyway, all this talking, let's get to working on it. We want to find the answer to these two questions. So the first one is the reaction spontaneous at 25 degrees Celsius? And the next question is, like, what's the minimum temperature? So believe it or not, I think it's actually faster to do B first, okay, because we can figure out A a lot faster, believe it or not. So to do this, of course, we need our equation. Our equation that we're going to use is delta G, Gibbs free energy is delta H, the enthalpy of the reaction, minus the entropy of the reaction times the temperature in Kelvin. Well, we have delta H, we have delta S. For question B, we're going to figure out what T, what is the minimum value, or that is to say, what value of T is like the threshold. Like once you go above that or below it, the behavior changes. So in order to do that, we want to set G equal to 0. And the reason is because if delta G is negative, it's spontaneous. If delta G is positive, it's not spontaneous. 0 is right between those, right? It's right next to negative, it's right next to positive. Which means if we can find that T value, then I'm kind of like, all right, here's a T that gives you 0. If we go above it or below it, we can figure out whether the reaction is spontaneous at high temperatures or at low temperatures, okay? And specifically, what temperature would that be? So anyway, plug in numbers in. Well, in this case, we're given them. So we have a positive delta H. This is an endothermic reaction. We have 178.3 kilojoules. Cool. Remember, it's minus delta S. Well, we have a positive entropy. This reaction increases entropy. So it's minus positive, so it's minus. Be very careful here. This is in joules per Kelvin. You got to convert joules to kilojoules because you can't subtract like apples from bushels of apples, right? They both involve apples, right? In this case, they both involve joules. But you need to convert joules to kilojoules. You could also convert joules to kilojoules or kilojoules to joules, but I think that it makes the numbers too big in my opinion, so it's just easier to convert to kilojoules. So how do you convert joules to kilojoules? You just divide by 1,000. So 160.5 becomes 0.1605. All right, and the unit here is now kilojoules, right? kJ per degrees Kelvin, right? That can be subtracted. You might say, what about the Kelvin? Well, we're multiplying this by T, which is in kelvins. That's how that gets taken care of. What we're going to do now is just algebra. We're going to solve for T, right? We're looking for what T value. So again, the algebra here, right, I could either bring this over, add this over, or I could subtract this. It doesn't make a difference. I'm just going to subtract this number here, the 178. So now I have negative 178.3 kilojoules equals negative 0.1605 kilojoules per degrees Kelvin times T. Hopefully you're saying, oh, easy peasy. Now all I got to do is divide both sides by, don't forget the negative, negative 0.1605 kilojoules per Kelvin. Okay. Hopefully you're aware that when you do this, obviously you got to do it to both sides, right? But more to the point, two things are going to happen that hopefully you're looking at and saying, oh yeah. Number one is the negatives are going to cancel. So we get a positive t-value. That's really important. If you got a negative t-value, it either means it's always spontaneous, like doesn't matter the temperature, it's always, or it's never spontaneous, doesn't matter temperature. If you get a negative t, it means it's either always or never. And if you're like, well, how do I know the difference? In my last video, we talked about this. Short answer is exothermic positive entropy, always. Endothermic negative entropy, never. Okay, but the math would check out. You get a negative t-value either way. In this case, though, we're going to get a positive t, so that's good. The other thing that's going to happen is the units are going to cancel, all fancy schmancy. Kilojoules go bye-bye. We're left with Kelvin, because we're dividing by it as a fraction. It becomes the numerator, which means t is going to give us a Kelvin answer, which is good, because we want that. So in this case, what do we get? Well, let's pull up the calculator, and let's see. So we have, again, I know it's negative divided by negative. I'm just going to make it positive because it's going to be positive either way. 178.3 divided by 0.1605. And we get an answer of 1100.9, we'll say. Okay, so 1,100 and, was it 10? Yeah, 10. 0.3, I think is what I said. I should really memorize these numbers. Oh, 0.9, sorry. So you think it'd be easy for me to remember numbers like that, but for some reason it's not. And this is degrees Kelvin. Now, you might say, okay, that answers B. How does it answer A? Well, so let's think for a second. This is the temperature that is when equals when it's neither spontaneous nor non-spontaneous. It's like that break-even point. And you might say, well, how does that help me? Because look at this. If T up here, which is positive, it has to be positive, is getting bigger and bigger and bigger, this negative number is going to get bigger and bigger and bigger. And eventually, if it gets big enough, if we subtract this whole thing from this, eventually we will get less than 0, which means the temperature has to at least be at least 1,110.9 degrees Kelvin. Notice the greater than sign. What we're saying here is if we're at this temperature, it's neither spontaneous not. If we go above it, even by 0.1 degree Kelvin, the reaction will be spontaneous. If I get hotter and hotter, guess what? It'll be spontaneous. Doesn't matter how hot you get it, it's going to be spontaneous. If you go below this reaction temperature, or rather below this Kelvin temperature, or this temperature in Kelvin, it will not be spontaneous, because if you look at the math, right, again, this is where critical thinking is important. If this number is not bigger than this number, we're going to have a positive answer, which means it's not spontaneous. And, you might say, okay, do I have to memorize that? I mean, I guess. I don't think it's that bad. But how about this? You could always check your answer. So you say, I think it's when it's at least this number. So plug in 2,000. If you plug in 2,000, you're going to get a negative answer. Oh, it's spontaneous. You plug in a number less than this. You plug in 1,000 degrees Kelvin. You're going to get a positive answer, which means it's not spontaneous. So you say, oh, it's got to at least be that temperature. Okay. Now you might say, okay, cool, but then how does this come back to letter A? Well, this temperature is less than this, isn't it? Which means your answer is, oh, it's less than the minimum temperature. It's not spontaneous at 298. Which means this reaction has to occur at least 1,110.9 degrees Kelvin for it to be spontaneous. Okay, that's the whole kit and caboodle. And you say, okay, kind of got it. All right, and be aware this is for a endothermic reaction that is positive entropy, right? If we had an endothermic reaction with negative entropy, you would get an answer, you would get a t-value that's negative, and you would say, which either means it's never or always, and in that case you'd say it's got to be never. Endothermic reactions with negative entropy are never spontaneous. Okay, if I had an exothermic reaction with positive entropy, then it's always spontaneous. But be aware, your temperature you're going to get in those cases would be negative in both cases. All right, so the negative just tells you temperature doesn't matter. But you need to know, you need to be able to say, it's either always or never, and that's the key, okay? Doing these problems, right, you just practice it a bunch of times, right? This is from the practice sheet I created to put on Canvas. Well, I used DeepSeek for it, which is pretty nice. Makes problems nice and quick for me, which is pretty nifty, right? But you always want to make sure it's right, check and make sure, right? But speeds things along, right, for worksheets and whatnot. Pretty nice, right? Good use of technology instead of just here's an answer, that's not good. We want to make sure we can think, all right? But yeah, hopefully this makes sense. Hopefully you're saying, yeah, that's not that bad. And again, I think at the end of the day, doing the math, yeah, cool, great, hooray. Can you explain it? Can you say, okay, it kind of makes sense why it's spontaneous at low temperatures or why it's spontaneous at high temperatures, right? If the universe does not like a reaction, if it's endothermic, right? Generally speaking, the universe is like, not a fan, okay? We've got to concentrate energy, okay? Exothermic reactions. Usually, we're a fan of those, okay? But if you reduce entropy, it's like, okay, yeah, but I'm not a fan of this part, okay? So we might have to do it at higher temperatures, right? You see what's kind of going on here, okay? That specific example kind of flipping it, right? Endothermic reactions want energy, exothermic reactions release it, okay? And this is going to play very nicely into what's called equilibrium, right? That these conditions we're seeing will affect whether a reaction wants to go this way or if it wants to go that way. Because if you flip a reaction, if you take that reaction, the calcium carbonate, if you were to flip that, right, you would find that that reaction is exothermic, and you would find that it has negative entropy, okay? And then the conditions change because the universe now has a different take on it, okay? The last bit here, and again, I got to keep it short because I said I was going to keep it short. I promised I was going to keep it short, is make sure you understand what it means to have high entropy, right? The exothermic, endothermic, I think is pretty easy. You say exothermic releases energy, it gets hot from our perspective. Endothermic is the opposite, it gets cold from our perspective. Entropy is harder. Think of it as, does the energy have a place to go? Is the stuff in the reaction going to help get rid of it, quote unquote, or is the stuff in the reaction going to keep it closer, take energy that wants to spread out and kind of keep it boxed in? The universe hates that, okay? If that doesn't happen, right, if the reaction is endothermic, is negative entropy, it means it's never spontaneous, which doesn't mean it can't happen. It just means something else is going to have to do it. It's not going to do it by itself. So maybe I have to do it. Maybe a plant has to do it, right? Photosynthesis is a reaction with negative entropy and is endothermic, which means it's never spontaneous. The plant has to have specific cells that do a job, right? Those chloroplasts, right? Doing that job, having specific proteins that line things up. It's like a little factory moving things around. That's not spontaneous, okay? But it still happens. It just takes a lot of energy. So hopefully this is all making sense to you. Hopefully it elaborates and elucidates for you, and you'll say, cool, I'm now an expert in rudimentary thermodynamics. All right, with that note, we'll leave it there. So have a great rest of your day.